Thanks everyone for coming. I'm glad to be here, and I'm glad you guys took the time out of your busy schedules to come and attend this. Yeah, as aforementioned, this is explainability, so data science and explainable workflows. And the way I'm going to be approaching this is from a high level kind of theory point of view, and then we'll dive into kind of a very brief example of something I put together for you guys to kind of showcase that this is not going to it's not going to greatly impact your workflow to the extent it's going to make things more difficult. It should actually alleviate issues and make things more resilient and reproducible, and have less drastic consequences on downstream tasks. So with that being said, we'll dive into it. Unfortunately, I'm using one monitor, so I won't be able to see your questions in real time. I'll circle back at the end, answer them to the best of my abilities. If I'm unable to answer them, I can give out my email and I'll follow up with you, or I can try and point you in the right direction. So once again, thanks everyone for attending. Saw we had a pretty diverse crowd, and I really appreciate you all being here. So let's start with, I know Tim brought it up, but if you like to go and get more kinds of this information, or different information on database structures, different data science routines, things of that nature, we have the community at ibm.com. Great resource. I post there. Other data scientists from IBM post there. Community members post, talk about problems that they're facing or cool things they've done. So I just wanted to give that a shout out because it's a worthwhile place to subscribe to. And that being said, let's dive into the content. So why are you guys here? You're here to understand what is explainability, how can it affect your workflow, and how can you use it to mitigate problems that can occur. So whether that's if you're in a highly regulated industry such as banking, or maybe if you're working on some kind of collaborative filtering for ads or marketing of that nature. The idea being this will be applicable to a wide gambit of different workflows, and also works with tabular information, works with time series, it works with images and natural language. So it's definitely not a panacea, but it's a great place to start. And so, yeah, let's start. You're here to, by the end of this, hopefully understand what this image means, what it helps alleviate, what are some of the downsides of using this, and how you can do it and port this to your work. That being said, we're going to work our ways to explaining this, but what this is an output from Lime, which is a explainability algorithm which perturbs your data set and will cast these changes and tell you, if you perturb your data set by this much, this is the overall contribution of that change. And that helps you at a high level understand what features are being used in your evaluation and how they actually lead to better accuracy, worse accuracy, things of that nature. It depends on what metric you're going for. So I like to start with this slide. I think it's kind of funny and it sets a good tone. So there are three kinds of lies. There's damned lies, and then there's statistics. No one really knows who said this, but it was popularized by Mark Twain. Another one that I'm sure everyone's heard, all models are wrong, but some are useful, by George Box. And then my favorite, why'd you do that? So you might hear that in your code reviews from management. You might get asked, why did your algorithm perform this way? That's kind of the catch-all of, what is explainability from an epistemological point of view? So, that's the theory of knowledge. That's what we're trying to capture. So as a data scientist, you're going to have your hands on tooling, information, data, resources, and what you do is a culmination of all these things to, effectively build some kind of machine learning, deep learning, or, for lack of a better term, AI system. And, how do you adequately relay what's going on to stakeholders, management, and affected people, so your end user. So the way I like to delineate these is these are normally coupled together, the idea of interpretations and explaining. I like to decouple them because I use them in a much more nuanced way. So what does interpret mean? This is the dictionary definition from Merriam-Webster. So interpret is to explain or tell the meaning of, present in understandable terms. The way I think of it is interpretation is it's a static thing. when you use anything from an sklearn pipeline to, a convolutional neural network, you interpret it, systemically. So, am I going to use dropout? What activation function am I going to use? If we're talking, deep learning, if we're talking machine learning, what data transformations am I going to make? What data am I going to need to use? So interpretation is this idea of, at each step you can look at, the output or your outcome and kind of evaluate, based off of my understanding of what I am doing and the underlying principles, does this make sense? So the way I think of it is, when you get 75% accuracy from your pipeline, that is something that you interpret, and that's why it's static. You don't necessarily explain it, because in explaining it captures this idea of that you understand where each thing happened, why it happened, and that's explainability. That's interpreting as, coming to the end, or coming to the end of a series of things, and then understanding this is what happened, this is what it means, and that should serve as, a kind of diagnostic, for lack of a better word, to alert you to things are going the way I thought they would, things are not going the way I thought they would, and then finding a way to remedy that if need be. Explain has a much broader definition from Merriam-Webster. It's to make known. To make what known? So as a data scientist, you're going to be in a pretty scrutinized area of interest from, like I said, everything from end users knowing, hey, I was on Google, why am I getting lawnmower ads, to, hey, I just applied for a loan and I was rejected, I'd like to know why. So it's to make known. I view this as a dynamic process. It's the idea of going through, an iterative loop of, once again, reevaluating that sklearn pipeline, or perhaps reevaluating your neural net. So if we interpret, hey, we see 3% gains in accuracy when we use max pool, or we get 5% accuracy gains from dropout, that would be interpreting it. But to truly explain that and be able to do causal attribution, you need to dynamically change things, play with it, make sure that, you didn't perturb your data set differently, and, the feature you thought that was affecting this actually has no effect, things of that nature. And the reason you do this is to mitigate, one, the fallout of things going poorly. So I'm sure everyone's read the news and seen where, certain algorithms have been discriminatory in nature, just, and people are unable to remedy. Is that by design? Is that from the data set? Is that the way these things work? And the idea is, if you do this dynamically, or, if you're doing it even better, recursively. So the idea of, you do this until you're finished, you reach your endpoint. You should, at the end of this pre-deployment, have a very good understanding of, where will this work? Where will it not work? What are the problems that can occur? How are we mitigating them? And how are we making sure that this is an equitable deployment, in which, people are, if this is something where it's, if you're using this to automate people getting loans or not, how can we make sure that this is happening in, in a fair and equitable fashion? Or, that's something that would have a high threshold for explainability. Or perhaps, if you're working in healthcare and you're doing tumor imaging, how would you adequately explain to the doctors who are going to use this, hey, this is why we know that our algorithm will be able to discriminate between a tumor and fatty tissue at X percentile. And, this is the testing, this is the documentation. One thing that can mitigate explainability is IP. So that is something, depending on where you work and the nature of your job, you may be limited to the extent you can tell people what you're doing because of intellectual property rights. But, if we're consuming this through an open source frame of mind, almost all this should be explainable. And and the reason I say it's an explainable workflow rather than, just shipping this as, a set of algorithms or things of that nature, is each project is going to have different stakeholders and different results, and it's also going to have a different workflow. But the idea being, the one thing that, constrains all of this is, you can create, kind of a decision boundary of, how am I going to do this in a way where I'm going to be able to explain this? Because I'm guilty of it myself, where I would just, you see a really cool algorithm, you want to test it out for yourself. And so the way you do that is, you get a lot of data, treat the data, throw it into the algorithm, what have you, whether it's, anything from sklearn to a custom C++ implementation all the way to deep learning. And then you get your results. And if your results are better, worse, or similar to the quote unquote state of the art, you throw it on GitHub and then people consume it. The problem with that is, in a productionized environment, is you're not necessarily just searching for the next best thing. You're searching for something that is going to, meet well set standards that you and your team set in place, and make sure that you are doing these things in a trustworthy and transparent fashion to the extent that you can. So once again, this is not a panacea. This is the idea that this is something that you can use to augment your workflow and to try and, save yourself some time and some, pain from having to, pull things off the production line, and also, help alleviate some of the downstream systems, downstream errors that can affect, your users. So once again, it's very easy to point to the news and see, quite a lot of things where, a lack of explanations have caused things to be derailed. But at the same time, we can take a more optimistic point of view, and we can look, to the media or news and things of that nature and see where these things have been implemented and where they perform well. So yeah, that's why I differentiate between these two words, because I think they kind of help create this philosophy of what are we actually trying to accomplish. We're not trying to, just use a new algorithm that's going to explain things to us, and then we can say, wow, we did explainable data science. It's really, from data ingestion to feature engineering to, model selection, all the way to validation. And what I've seen as I go into the literature and evaluate these different, systems and look at different projects is explainability does have a very, very large concentration of literature and effort being put into this kind of model validation side, which is, kind of the latter half of data science. So, accommodating for things like data drift and, things of that nature. So how do we boil this all up and package it? Because we don't want to boil the ocean. So this is my definition of explainability. It may differ from other people's, but we define explainability as the ability for a data scientist or another IT professional, whether you're a data engineer, things of that nature, results to be understood and interpreted by other data scientists and stakeholders. So the way I think about it is, the simplest way you could put this is like if you've taken a CS class and you do some kind of sorting algorithm and you're trying to understand, the difference between different sorting algorithms beyond, just big O notation of speed and scalability and ease of use. You're trying to understand the underlying implementation, where it performs well, where it does not perform well, and where one sorting algorithm may perform better than another. But once again, this is in a well-defined context of a classroom where you normally have a professor who's well-versed in these things, who can, correct you if you're wrong, lead you down the right path if need be. But, as a data scientist in the wild, you may not have someone who knows the outcome of this problem solution. They may not know what is the best suite of algorithms to use. So that's why we try to use this idea of explainability as, bounding this decision space. So if I want to make sure what I'm doing is trustworthy and transparent, that kind of mitigates some of the steps I can take. I'm not necessarily going to just take all the data and throw into XGBoost. You can, as a prototype, but I don't think that, the time you save in doing that from, creating your own custom solution can actually lead to, more costs in the frame of, time, talent, and treasure downstream, because you didn't do some of these steps that we incorporate in this workflow. So that's the main idea to, motivate this stuff. And then the second half of this talk is going to dive into like a very brief example. It's not like a pre-built demo that I can give you guys the links if you want to see it. It's I pulled data online and we did an explainable workflow on it to, try and understand why we're getting the results we are. Once again, it's not, a super robust or a crazy one, but it's relatively robust, but it's not super crazy or super detailed. The idea being is I'm trying to show you how you can incorporate this. And if you want to take it to the nth degree, I'll give you my email at the end and we can talk more of how this could work in your workflows. But once again, this is just how can we show the most people how to effectively do explainable data science in the context of their workflow. So I know I've been saying, like, before you start this stuff, before you put hands on data or make data requests or, put your fingers on a keyboard, you should be sitting with your stakeholders, whether that's, executive level, your manager, maybe perhaps an end user, and try and understand, like, what is our decision space? Think of this as a math problem that you do in school or that you do on an online course where they tell you, like, the realm of the solution space. And once again, in data science, the solution space could be everything from, a decision tree to a neural network to a rule-based system. What I find better to do at the beginning rather than at the end is, define this decision space. How do you take a weakly defined problem, which could be, we want to spend less money on marketing, so we are making the decision to automate it. That's weakly defined in the sense of, how are you going to track and measure that you're actually doing better than you were before? How are you going to make sure that it's being done in a transparent and trustworthy manner? And how are you going to make sure that, people are not being adversely affected and the business is not being adversely affected? Because until you deploy it, you have a good idea, but things can go awry. And so that's, once again, we want to define this, narrow it, so when things do go wrong, we understand. So what this graph is trying to, elucidate is, it goes from -5 to 5 on each. So now you can think of it as a bounded decision space. It's not going to escape from -5 to 5 on either end. So there's discrete values. And what I did is I plotted a few different individuals. So you have a data science manager. So if the y-axis is technical skill, the x-axis is experience, and the z-axis is need, need being like the need for an explanation, a data science manager is a 4-4-4. They have enough experience to be a manager. They have enough experience to be a data science manager. They have the technical skill to be a data scientist, but they also have a high need for these explanations because they're the one who is overseeing the work, and it would be, in my eyes, asinine for them to be able to put their stamp of approval on something that they don't adequately understand. Conversely, you may have an end user who may not have experience in the technical world. This could be anyone from someone working in retail to, a mechanic to another data scientist. We don't really know, but for the point of this, for this talk, we're going to imagine that they're not necessarily experienced in data science. Their technical skill, most people nowadays are relatively technical because we have, these things, smartphones, but their need is high. Someone is going to be, someone is applying for a loan and they don't speak to a person throughout the process, but then they're rejected. How do they remedy that? And on top of that, if there is no suite of explanations, when they do get in contact with a person who just sees their final evaluation, how do they know what steps they can take to improve? How are they able to compare, if Bank Z and Bank A both reject me, but Bank Y doesn't, where was the difference? And if you can't explain that, maybe Bank Z doesn't use your credit score. They just use historical payment data, or maybe, so once again, there's a wide gambit of reasons, but as a data scientist, your job is to not only build out the system, make sure the system functions correctly, but to, empower your stakeholders, your managers, and your end user to make good use of these systems. And then, we have a data scientist who's, got relatively good experience, relatively high technical skill, and they sit somewhere in the middle of need. The idea being, and this is encapsulated in this workflow, you should be able to, work with the other data scientists. You don't want to silo yourself. So you want to be able to say, like, hey, these are the reasons I made these decisions. These are why I think they're good decisions. These are why I think they're going to lead to, positive outcomes for both the business and the end user, or whoever's going to make use of the system. And, you want to put that into a frame of reference where another data scientist could perhaps say, well, I agree, I disagree, I'm neutral, I don't have enough information, things of that nature. And then the last persona that's on this graph is a regulator. So if you're working in like healthcare, financial industries, even just, like pure tech. Uh, if someone in a suit and tie knocks on your door and says, "Hey, we need to understand what this algorithm's doing. We know you're protected by IP, but we're going to go and talk to your data scientists." If the only person who has the high level view of how these things work and where they're being used is the manager, the executive, if they speak to the person who built it out and they don't have this information, or they're unwilling to share or unable to share, I'm sure you can all imagine how that could become problematic. So we're going to dive into some code. So what is this example? It is the Portuguese banking data set from UCI. The problem is to classify users if the bank term was opened, yes or no. And then we want to identify the principal factors contributing to this classification. See, this is an area where if you're working with data scientists, you could work and talk, say like, why are we gonna classify them rather than just predict? Classifying removes the actual decision maker from making a decision, because classification encapsulates this idea of making some kind of choice versus just predicting and being able to see and then having a human evaluate it. So that's what I mean by an explainable workflow. So like, as soon as you get your problem statement or your data, you should be evaluating, what are we going to do? Why are we going to do it? Why is it better than choices B, C, and D? And then once you have buy-in from your stakeholders and the people you need it from, that's when you should start, the explainable process, of codifying these things. So, okay, let's go to the code then. So this is where I got the data, just so everyone can look. Brief description of what the data set is. So we have 20 different features, and then the output variable, our target, is binary. Did the client subscribe to a term deposit? We have things like age, job, marital status, things of that nature. The one I want to focus on, Euribor 3M. So it's the Euribor 3-month rate. So this is something that happens in the EU. They use it. I'm not going to go into detail. It's something you should look into more if you want to see what it is. But that's something I just want to point out, and you'll see why. But this is part of explainability, understanding how is this data collected? Why was this data collected? What does this data mean? Why did the features take the form they do? So as you can see, we have Boolean values, we have categorical values, we have numeric values. We have a wide gambit of data, and we should double check with the stakeholder. Where do we get this data from? Why are we using this data? Is there any PII in this data that we need to make sure that we're mitigating against or properly using? So as you can see, this starts as soon as the project starts. You should start documenting these things, not only to protect the business, protect your end user, but to protect yourself. Make sure that you are performing in good faith and to the best of your ability. So with that being said, it should be big enough for everyone to see. I hope so. Ignore that. This is on the cloud. So, but yeah. So this is Cloud Pak for Data. This is an IBM. It's an IBM piece of software. This is Watson Studio Cloud. So I ran this, in the cloud, not locally. I did this with like 2 gigabytes of RAM and 1 CPU. So it's pretty robust. None of this took too long to run. I do have this on a GitHub I can point people to if they want to clone this. The GitHub version goes into much more detail, but once again, in an hour, I didn't feel like I needed to show you every visualization, every single thing that you can do, because once again, this can go to the nth degree. And I don't want you guys to be bogged down. I'd rather you be able to take the high level overview of what are we doing, why are we doing it, and how can you take it and apply it, rather than just listening to me talk about it. So the main tools we're using are Lale and AI X360. These both have accompanying GitHubs that I can point you to. If I remember correctly, it's just like github.com/IBM/Lale or AI X360. They both have their own suite of examples, use cases, and validation, and they both have accompanying academic papers. What's important to note is 2 things I didn't use in this, just because they are difficult to relay in this amount of time is AIX 360 comes with 2 explainability metrics. I'll just give a high-level overview of what those are. So one is faithfulness. So when you use an algorithm like Lime, which makes perturbations, and by perturbation I mean, if this number is 93.994 and we get a Y of no, Lime is basically going to change this number to the extent to see if it changes our classification through our algorithm. If it does, then that would indicate that consumer price index, it carries X amount of value. That's what faithfulness does, and it's a Boolean. It's going to tell you true or false. No, it's not Boolean. It's from -1 to 1. So it'll tell you the level of agreement between the explainability algorithm and the actual algorithm doing the computation. The other one is faithfulness, monotonicity. That's the Boolean one. So what monotonicity is feature 1 through feature n. If you use each feature, is it I can never say this word, monotonically additive. And what that means is, does each one of these features carry additional information to the algorithm? So if it's true, then that means you kept the right features. Each feature is leading to a gain in whatever metric you're using to evaluate, whether that's an F1 score or just accuracy. If it's false, that would indicate to you that perhaps you need to go back to feature engineering and see, is there a way to remove some of these or maybe do better feature engineering. And the other way you can think about it is when you are doing these computations, less is more, once you're deploying it, if you're using some kind of cloud system and you're paying for the hour, paying per compute, the less compute you do, the more money you save. So explainability, once again, is not something that you just use to service your stakeholders and your end user and make sure that they can believe in what you're doing in a trustworthy and transparent manner. It allows you to believe in what you're doing, which is very important because as a data scientist, some projects can quickly get out of hand and you can be left saying, I'm not sure where I went wrong or where I went right. How do I remedy this? Even with good documentation and notation. So once again, this is a workflow because this is tooling that is meant to help you, not hinder you. But with that being said, let's kind of dive into the code. So, we read in our data, separate it by a semicolon. We use label encoder to make sure that we can turn everything into a numeric value. This is pretty, boilerplate code. I'm sure most of you have seen this before. So encoders from sklearn, we copy our data over. We drop, we drop our independent value, our dependent value, and then we have we transform it. And then I did an 80-20% split. So the training length is 80% of the data. The test data is 20% of it. You could change this as you see fit if you want to just copy this. So, we cast it to train X, train Y, test X, test Y. We encode it. And then we have a correlation matrix. Once again, I'll show you the GitHub at the end if you guys want to go visit it. There's much more graphics where, we do histograms and we analyze each feature by itself and see, are there any statistical anomalies, things of that nature. But for the high level overview of what we're doing now, a correlation matrix will suffice. So this will, this is going to indicate, along the diagonal, of course, each feature is correlated with itself. But, what we're kind of looking out is for, these ones up here, these red ones. So as you can see, employee VAR rate, that's highly correlated with the consumer price index, things of that nature. And we use this to inform, what are we going to drop? So what did we decide to drop? I decided for the point of this one, I wanted to drop age, housing, the loan, default, and the day of the week along axis 1. And now we can describe it and we do info. And the reason we do info is I wanted to make sure everything is in an N64 format. So that way, when I put it into my algorithm, I don't get errors of, because Python's dynamically typed, if you don't cast them properly, that can lead to problems. Ignore importing OS. When I ran this locally, I just did this so that way I can make sure the graphics library was there. So we're going to use, so Lale is built on top of sklearn, so you can use basically everything that you're going to find in Lale straight from sklearn or vice versa. And if for some reason there isn't a algorithm you want, there is components to allow you to do custom wrapping so you can fit, a utility function in or what have you. It is important to note that XGBoost is no longer contained in Lale in the pip version. If you install the full version or install from source, XGBoost will be contained. It can be problematic on non-x86 systems. So that's just something to throw out there. And then from AIX360, we import Lime, and then we're going to use SHAP as well. So the idea behind this, the reason I incorporate this into explainability as a workflow is, as I said, you can spend a lot of time on algorithm selection, fine-tuning algorithms, things of that nature. What we're doing here is, and as you can see in the visualization, is we want to make a union, so no operation in PCA. We're going to concatenate those features, and then we're going to select from these 4 algorithms. So random forest, XGBoost, a logistic regression, or a decision tree. And this is going to happen in an automated way. And what this is going to do is it's going to quickly indicate which one's going to perform the best. And it's going to allow you as a data scientist to free up some time. And then, once you get the quote unquote best one, that's when you can go and begin fine tuning and saying, hey, can I use less data? Can I use more data? Can I, fine tune this to use less compute, things of that nature. So, we run this, the color indication does, it indicates what has been selected, what is still mutable and immutable. If you go to the Lale GitHub, there's 4 colors. There's like white, cyan, dark blue, and an even darker blue. And they all mean different things. They just tell you if they're in a trained state, a trainable state, if they're mutable or immutable. So once again, we make sure we have our data set up. This is where we actually train the pipeline. So as you can see in 3 lines of code, or technically 2, we're able to configure. And this works with all kinds of optimizers. It works with HyperOpt, it works with SMAC, and it works with grid search. Those are all going to give you different solution spaces. But the point is, if you use the same optimizer and you copy this and run it on your computer, it will be resilient and robust, and you'll get the same results. Also, all of this can be ported into a JSON format. So the data set can be ported into a JSON where you have all your types for each data, their value ranges, things of that nature. The configuration also allows you to do cross-validation and set your maximum evaluations. So I did 10 max evals, 3 cross-validation steps, and our best loss was 0.93 or negative 0.93. And it took around 11 seconds per trial. So we ran through, a PCA, concatenate the features, and 4 different algorithms, 11 seconds, 10 times. So it's like, 110 seconds, so less than 2 minutes. And this was 2 gigabytes of RAM and 1 CPU. We can visualize which one we selected. So I'm pretty sure, as most of you probably would have guessed, XGBoost ended up doing the best, which is a gradient boosted tree. And we got 72% accuracy out of the box. Once again, this is not explainable, but what this does is it frees up time. So now that you have the idea of like, this is probably the best algorithm I'm going to use, maybe I drop these other 3 and I run XGBoost against a more complex algorithm, or maybe a rule-based algorithm, and see what I get. And then once again, this step is interpreting it. So we get 72% accuracy. That's pretty good on our test set. To make this explainable, we should maybe pause here, rerun everything, make sure it's resilient and robust, like I'm telling you it will be, and take some of your own steps, some of your own best procedures, or some of your team's best procedures to make sure that you're evaluating this in a contextualized way, and once again, operating within a trustworthy and transparent manner. So this is Lime, so Lime tabular explainer, because this is Lime values. I'm not really going to go into what we feed it. What's important to know is we feed the values, class names, and the feature names, and then we discretize it. The class names are for the value we're predicting. The type is it's a class, so it has underlying, has what is the word I'm looking for? Has underlying components that you can call and use if you see fit. I didn't go into that because once again, it's an hour-long talk. But we explain our pipeline. So we pass our values in for the index of 10. We use predict Bravo, which is from sklearn. We tell it the amount of features we keep, and then we give it its class names. And then we show a notebook. And then if you remember from the first slide I showed you guys, this is the evaluation. And what this is indicating is Lime is for this value, its actual value is 0. We get a 93% classification for it being 0, 7% for it being 1. And this tells you, I'm not going to go too much into the math, but log odds are the inverse of each other. So if duration sits between, if duration is greater than 175, which is the seconds of the call, it's going to lead to a 5% increase for the classification of it being yes. Conversely, if it's not, it's going to be for 0. And then same thing with Euribor 3M, which is the 3-month Euribor rate, which is like it's a percentage. Once again, if you want to know more, look into it. But that's part of explaining, So if you were to show this to someone and they ask you, hey, what does this mean? You would want to adequately relay that. And perhaps this is data that isn't from the web, and you would need to go and find someone you work with and say, hey, what does that actually mean? Hopefully that's not something that happens while you're doing this. This is something that would happen while you talk about your solution space and set up your decision boundaries at the beginning. And then this is the actual feature and value for this index. So we can see based off of these, where do they fit in these less or greater than, and do we have good faith that this is an adequate explanation? And once again, this is a workflow, so this is something you could interpret once, go back, iterate through it, make sure that it's convergent, and et cetera, et cetera. But this is just a high-level way of doing things. And then we can use SHAP as well. There's a kernel explainer and a tree explainer. There's an accompanying paper for this if you want to look into it. SHAP values come from economics. Once again, it's a class, so it has underlying calls you can make to it. So we explain the instance of all of our data. And then we initialize it in JavaScript. We force plot it. This indicates, we get a 97% vote from SHAP that this is this value. This indicates that these are the most important values, so Euribor 3M and the duration of the call. And these are going to indicate to you, how much information do they contribute. Another way to plot it, and I like this one a little bit more because it's easier to understand. I'm just showing this one because this is one that you'll see in a lot of the literature, and you'll see in a lot of online examples, is this waterfall plot. So duration to get an f of x of, so our prediction of 97.4 or 97.4% that this is this classification. Euribor 3M contributes 5%, this contributes 9%, and our baseline of expected value of f of x is 0.832, which indicates that our data kind of either confirms that they opened it, or if these values were to be flipped, they negate that prediction or classification. And yeah, so once again, if you guys want to dive more into the literature to understand it, I can share with you resources, or you can talk to me offline. But the idea is this kind of encapsulates a workflow. So what we did is we went through it together, we interpreted the things, and now if we want to make it explainable, we could rerun it again, make sure that everything's working, change some things up, and try and diagnose, if I change X in my pipeline, how does the contribution of Euribor 3M change? Or how does our accuracy change? Things of that nature. So with that being said, I'm going to go back to this. These are some of the papers I recommend you guys read. So Stop Explaining Black Box Machine Learning Models for High-Stake Decisions. This is from Cynthia Rudin over at, I think it's Duke. Explainable Artificial Intelligence. This is from DARPA. It's a program update. It tells you about why is explanations important, who's doing it, where, why should I trust you, explaining the predictions of any classifier, type-driven automated learning with LALE, that's from IBM, towards robust interpretability with self-explaining neural networks, that's an MIT paper. That one's pretty heavy on the math, but it's interesting. And then TED, teaching AI to explain its decisions. That's another IBM talk or paper. And then where the demos live. So the demos live at the Bluemix site for AIX 360. That takes you through some like well-curated demos. The actual source is at github.com/IBM/AIX360. The Lale GitHub is at github.com/IBM/Lale. And then there's an IBM masterclass that ends on the 18th. And that has like an hour and a half of content that goes through kind of what we did in this talk, but in a, in an hour and a half. So you have more time to understand each one of the sections, replicate it. And then, there's a quiz at the end to, help indicate to you if you got the high level insights from it. That's what the masterclass looks like. So if you want to go there, there's going to be like a week and a day left of it before it moves. So maybe go give that a check out. And then this is the bibliography. So yeah, okay, yeah, she is from Duke. These are the resources. I can send you these papers if you want in PDF format. And that is it.
Great. So we have some questions in Q&A. Maybe we can go through that.
Sure.
If you click, you can click the Q&A and then see that, or you want me to read it to you?
The 3 Q&A. I was reading.
Yeah, you can just click a Q&A to see that. It's probably easy.
Why did you not choose to drop the most highly correlated features? That's like that. So the point of that example was showing that the workflows can be relatively easy, and my idea was not to make like the highest accuracy model I could. The idea was to show you like where decisions can be made. So that's one of the questions that would make this explainable. So why did I not drop the highly correlated features? So when I did this originally, I went through and I did different sequences of like transformations and dropping and change, and saw I was able to get a half a percentage point increase in accuracy and things of that nature. So at the end, I decided to only drop the ones I did because it was less typing on my end and I was kind of being lazy. But it is something where if you wanted to download it and replicate it, you could drop more features, drop less features. And I can point you to that where that GitHub actually lives. I joined a bit late. Where is the link to the source data? I can just drop that in class. I can just drop that in the chat. Chat. Wait, how do I chat? Oh. Here's the data. Okay, thank you. Neural networks are sometimes thought as black box. Is there any progress on the explainability of an artificial neural network? Anywhere I can get a start? There are. So the AIX 360 library has a thing called DIPVE, which is directly interpretable variational autoencoder. That one's pretty mathematically heavy, so that's one of the ones I chose not to go over, but that's a good place to start. It is on their GitHub. That MIT paper also goes over it, and it kind of talks about why they're not black boxes and things of that nature. But I think the important part to understand of a neural network is that the computations, of what we're doing is like, weight times X plus a bias term. The idea behind these are well documented from like the 50s and 60s with the advent of like perceptrons, and then we understand the limitation of perceptrons because of the XOR problem. So the idea being is neural networks are explainable to the extent we understand the underlying assumptions and mathematical nodes and models that are being computed. The problem is when you expand that to, so like GPT to medium, which is like the NLP thing that's taking the world by storm. When you expand that to 333 million parameters, you can have an understanding of the principles and assumptions that are being met or not being met. That being said, when you explode it out to that level, it's hard to articulate, one, how you'd go about explaining it, and secondly, even if you did, how would you explain it? So yeah, so I understand why where that question comes from, but right now, that Cynthia Rudin paper, she kind of says, don't use black box models, so don't use deep learning or artificial neural networks anywhere, because you can get similar, if not better, results with a handcrafted rule-based system. The problem being the amount of the level of expertise to build out a rule-based system like that kind of offsets people's interest in them, because to get, you know, a panel of 15 experts is quite expensive and their time is valuable. So I hope that helps with your question. But if I were to start that, there is like integrated gradients and things of that nature. So Facebook capped them. I can throw that in the chat maybe. Facebook capped them. Oh, my GitHub is github.com decent dilettante. And that's where that stuff lives. One of the earlier charts was showing scale, expect 5 on the explainability scale. Oh, I might have put the wrong number for them. I meant that to be a need. So the idea was like, if you work in financial industry and you're rejecting and accepting people for loans, and you have a, you know, the SEC come by and they're saying like, hey, how are we making sure that this is not acting in a discriminatory or predatory way? Their need is high to the extent like they're the government. They can come there and say like, hey, you're not meeting our criteria, we're shutting it down. And then the other thing is with regulators, they tend to have well vetted and people with a lot of experience who will come and do these things. That's not always the case. Sometimes it can be someone who isn't that experienced, but normally they're going to send in someone who knows what they're talking about and knows what they need and knows what to look for. So that's kind of why I put them. And once again, those were like imaginary numbers, because you know, it's hard to group people just like, you know, based off of their occupation to their skill set. So like, as we all know, there's some data scientists who are more technical than others, and there are some, you know, managers who are more experienced than others. And so I was, you know, trying to use one point to demonstrate a persona that's made up of a lot of people. So I made a generalization. Is there any difference in approach based on the problem you're trying to solve to address explainability? Yeah, I mean, so originally I looked at explainability very much through like a coder's lens. I was like, what algorithms can I use? And now conversely, I'm reading a lot of papers from like the 50s and 60s and 70s from like cognitive psychologists and neuroscientists and things of that nature, who were studying like, what is an explanation? How does one serve an explanation for the highest degree of impact? You know, moral philosophers and logicians who are saying, you know, things like, you know, like what is the antecedent and what is the predicate and how do we arrive at this conclusion? And if you demonstrate it this way versus this way. So the idea was not so much of like using explainability as a single source of like, aha, I gotcha, here's the algorithm. It's more of like, hey, here's a workflow to best reach your goal. And your goal is to, you know, do these things in a trustworthy and transparent manner. And so my idea being is use the best tooling you can, use your best judgment, and make sure that you're, you know, we all stand on the shoulders of giants who've done a lot of work to get us to this point. So make sure that you're doing them justice by, you know, doing your darndest to make sure we're operating in a fair and equitable manner. Can you please share the repo for the Jupyter notebook shown in this class? Yeah, it's in github.com/decent dilettante. I can type it here if you want.
Is that one is already posted in the chat, right?
Yeah, I think it is posted in the chat.
Okay,
so.
I will repost it again. By the way, we have attendees raise a hand. She or he probably want to speak to ask questions. Let's give them a chance. Hey, it's D1, and you are unmuted. If you have questions, you can speak.
I think you're on mute.
Yes, but he or she need to unmute by themselves. Hey, D1, can you hear us? Okay, never mind. You can continue for the other questions.
Can you share the repo for the Jupyter notebook shown in this class? Yeah, it's at github.com decent dilettante. It's under like the XAI part. And then, and I can send it to the presenter if he wants to post it with the replay. And then where would stakeholders like executives and consumers for bank loan So at a place like IBM, a lot of our executives are deeply I mean, at least where I work, they're deeply technical and they have a lot of experience. And yes, they have a lot of experience. They have a lot of need, and they have a very high technical aptitude. So they'd probably be like a 5.55. Like there are people who pass all the technical litmus tests. They understand where these things are going to be used, how they could evoke positive or negative emotion, where they can be used well, where they'll be used poorly. And on top of that, they are held accountable by everyone by nature of their title and job duties. So yeah, I think they'd be like a 5.55, at least IBM. So I'm a little biased, but they're pretty smart. I missed the link for ANN Explainability Work by Facebook. It's called
that one, I think I already reposted before you post to the panelist only. So I
okay, yeah. So that's in the chat. And then
yes, in the chat.
Answer my query. Can you briefly explain and share ideas on the NLP type of problem, multi-level classification, for example, for explainability? So that's something where like I mean, it's based off of so for a question like that, there's a lot of like assumptions that would need to be made for me to even give you a good answer. So maybe that's something like if you want a good answer from me rather than just like a very general like this is where I'd look, maybe ping me or email me. My email is my last name at ibm.com. And then we could talk more about that. There are ways of accomplishing that task, but it's a combination of pre-processing, post-processing, and everything in between. So in the interest of time, I would just say maybe hit me up on LinkedIn or hit me up on email, and I will do my best to help you with that. But good question.
Great. Do we have any other questions? If you have questions, you can. We have a couple more minutes. You can post the questions in the Q&A or raise hand. I will let you to speak to ask. Have another one coming in the Q&A.
So is there any US or EU regulation that explicitly requires for a machine learning model to be explainable? No, I mean, we're making our way there. I mean, the caveat is the EU has GDPR, so protecting personal information. Same thing with the US. So to that extent, like there's very explicit guidelines of what data you can use, how you can use it, where it can be used, and to what degree can it inform a decision. But to the context of like, you know, no one's going to go to right now. To the best of my knowledge, there's no law or regulation that says like, hey, if you are a ad-based marketing agency and you use quote unquote AI to do ad placement, there's scrutiny involved, but there's no one who has to say like you have to explain how they got that. And that kind of falls under like that NLP problem I was asked earlier with, when you explode these things. So like, I'm sure people know what page rank is and like how things are pushed to you. But when you explode that to, billions of pages and billions of users in real time, that's hard to explain. It's difficult and there's limitations, but to the best of my ability, I don't think there's anything besides like data protection acts and making sure that you're not, putting out hostile software. So maybe that's something I can do more research into and give you a better insight. But once again, to the best of my knowledge, I'm unaware of things besides protecting people's private information.